Good morning, future presidents. Today we are starting on nuclear energy. So this lecture and next lecture are covering nuclear energy and nuclear weapons. This is one of the key topics we've been working up to in the class, so I'm looking forward to covering this. I already made a post on this on the boards, so next Tuesday's lecture is optional. It won't be on the final, but it's going to be about Big Bang, which should be really cool. So, you know, I would stick around for that, but then again, I'm kind of a geek. Okay, so today we are starting on nuclear energy, and we're going to start with nuclear structure. So we already talked about this a little bit in an earlier lecture, but let's review just a little bit and then move forward from where we were. Okay, nuclear structure. Remember that the typical size of an atom, which is set by the electrons, is on the order of 10 to the minus 10th meters, which we call an angstrom. And that is set by the electron orbits. Okay. The size of the nucleus, so the part that holds the neutrons and the protons, is about 100,000 times smaller than that. So the typical scale is on the order of 10 to the minus 5, 10 to the minus 15. 10 to the minus 5 is actually, visible on the desk. 10 to the minus 15 meters. So that's a femtometer, and that is set by the tightly packed neutrons and protons. Okay, so it's impossible for me to draw a picture of that even to scale up here, but let's draw a little model of an atom with the electron spinning around. And in the center, there is the nucleus, which is 100,000 times smaller than the size of the electron orbit. And if we blow that up, the nucleus would be a tightly packed configuration of neutrons and protons. Okay. So that's the core. Now the mass, remember the electron is about 2,000 times less massive than the proton. Neutrons and protons have almost identical masses. And so typically for an atom, 99.98. Okay. That is for larger atoms, but this is a good rough number. So typically about over 99.9% of the mass is concentrated in the nucleus. So while the electrons have a very big role in the size of the atoms, and of course the chemical structure of the atoms, the nucleus is where the mass resides, and also where most of the energy resides in the nucleus. In the atoms themselves. Okay, so let's differentiate between an element and an isotope. Okay, so an element. So we all know the elements: hydrogen, helium. You can go up from there. It's been a long time since I took chemistry, but we know the periodic chart. All of those are the elements, and that is defined by the number of electrons. So the number of electrons that are orbiting the nucleus define the chemistry of the elements. Okay? So the element is defined by the number of electrons, which equals the number of protons. you have an atom flying around that has that's missed an electron, then that's missing electrons, so it has more protons than electrons. Remember, that's a very strong force, the electromagnetic force. It will find an electron, and it will become neutral. So atoms in general are neutral unless they are very, very hot. Okay? And the chemistry is defined by the number of electrons, which is equal to the number of protons. So that defines the chemistry. Okay? The number of protons determines the chemical nature of the atom. Okay? You want to separate that from, let me do an example of that. So example, which will be important for the rest of this section, is uranium. So uranium, sometimes we see it written as U with a little 92 subscript on it. That subscript is the number of protons that the uranium atom has. So uranium has 92 electrons, 92 protons. For an element, for an atom of uranium. Okay. Now we're going to differentiate that from an isotope. Okay, so we differentiate an isotope from an element by the number of neutrons. Okay. Even though a uranium atom always has 92 protons, in the nucleus, we can vary the number of neutrons in the nucleus. And depending on how many neutrons there are, we have different isotopes. So chemically, uranium is always uranium, but we can differentiate the number of neutrons in the nucleus and produce a different isotope. So it has a different mass, but it has the same chemical nature. So an isotope is determined by the number of neutrons. In the nucleus. Of a given element. Okay. So generally, just for a rough number, the number of neutrons is 1 to 1.5 times the number of protons. In the nucleus, we're going to talk about that a little bit more in just a few minutes. That's a general number. For most elements, for most isotopes, there's generally 1 to 1.5 times as many neutrons in the nucleus than there are protons. Okay, and that will be more apparent in a second. So let's do an example of this. Another one that will be important for the rest of our discussion. So there are two very important isotopes which we're going to talk about. One is uranium-235. Uranium, it is uranium, so all uranium atoms have 92 protons. Okay. So uranium-235 by default has 92 protons. Okay, and it has 143 neutrons. Okay, so if we sum those two numbers up, we get 235 what we call nucleons. Nucleons just means a neutron or a proton, anything that's in the nucleus. Okay, uranium-235 has 235 nucleons, so 235 neutrons and protons. And because it's uranium, it means it always has 92 protons, okay, which means there are 143 neutrons in uranium-235. Okay. For comparison, we're also going to hear a lot about uranium-238. Okay, once again, 92 protons. Okay, still has, it's defined by 238 nucleons for uranium-238, so that means we've got 146 neutrons. So 238 nucleons total. uranium-235 and uranium-238, which we're going to hear a lot more about. Now, something very important about these two isotopes is that they are chemically identical. So if you put either of those isotopes into a chemical reaction, you're going to get the same reaction out independent of the isotope. Okay? That's because the chemical reactions are determined primarily by the electrons. Okay? And these have identical electron structures on the outside. So chemically, these are identical, but they are very different in nuclear reactions, which we will see. Okay, so chemically identical nuclear reactions are almost are very night and day between these two isotopes. Okay, so some isotopes are stable. So a lot of people, when they hear the word isotope, they immediately think radioactivity. Okay? But that's not true. Most isotopes, or at least most of them in the world around us, are stable. Which means they never change. Okay, so if we have an isotope of, say, carbon-12, which is very stable, it never changes. Okay? It always stays carbon-12. And some are unstable. Okay, and the unstable ones will undergo radioactive decay. Okay, and during the process of the radioactive decay, the nucleus will actually change. Okay? Doesn't always change into a different element, but they can change into different isotopes. They can change in different elements. Sometimes they just decay by releasing energy, which we'll talk about, and they don't actually change the nature of the atom. Okay, generally when isotopes are undergoing radioactive decays, they're trying to get to a more stable state. Okay, and we'll talk about that. So generally the nucleus, there are competing forces going on, and they're trying to decay into a more stable state to alleviate some of those internal forces. Okay? But before I talk about that, let's talk about the half-life. So when something is undergoing a radioactive decay, its decay time is characterized by this quantity called the half-life. Okay. And the half-life for an isotope is the time for half of the unstable isotopes in a group of isotopes to decay. So the half-life is the time for one half of the unstable isotopes in a group to decay. Okay, I underlined the statement in a group, okay? And the reason is that the half-life for a single nucleus actually doesn't make any sense. It's not defined, okay? The nucleus, when they decay at a random time, and you can only define sort of an average time or a half-life in terms of a group of many different particles. Okay? So, which individual nucleus decays at which specific time is completely a random process and one that we can't predict. Okay? So you can only look at groups of nuclei and discuss their decay, the typical decay time for that group as a whole. So let me give you a very concrete example of that, which will also be important as we go forward. And that is the neutron. Now, this might be surprising to some of you, since most of you know a little bit about nuclear structure from high school classes or just from the general press, that nuclei are composed of protons and neutrons. Okay? In nature, neutrons by themselves are actually radioactive. They decay. Okay? They're only stable when they are bound up inside of a nucleus. So if we have a free neutron, it will decay with a half-life of 10 minutes. So let me write down this. Neutrons in nuclei, and I'm going to write they are generally stable, but free neutrons decay. Okay, so free neutrons. We do not have a lot of free neutrons running around in nature, and the reason is because they decay with a very short time. So they have a half-life of about 10 minutes. Okay. Which is not a very long time. Okay. And they undergo this decay process where a neutron will decay into a proton plus an electron. Okay? Remember, the proton and the electron have opposite charges. The neutron has a zero charge, electrical charge I'm talking about here. And so the neutron, when it decays into a proton electron, there's no charge that's created, no net charge that's created, but it has split into these separate positive charges and negative charges. Okay? They're equal and opposite. Okay, so let's draw just a picture of what this might look like. So let's start off with some group of neutrons. 2, 3, 4, 5. Okay, let's say we're starting off with a group of 8 neutrons that are free, so they're not bound into a nucleus. So we've had some nuclear reactions. It's important in nuclear reactors, for example, where we have free neutrons running around. Okay, and then we wait for 10 minutes. And what we see is that we cannot predict what any individual one of these nuclei will be after 10 minutes, neutrons will be after 10 minutes, but we know on average that half of them will have decayed into protons and the other half will not. So we'll have some structure after 10 minutes where maybe maybe these two have stayed, then we've got proton, neutron, proton, 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 neutron. So where half of them on average is decayed. So I drew this with 4 here after 10 minutes. It might be 3. It might be 5 that have decayed. So on average, we can't say. So if we wait another 10 minutes, then these protons are now stable, so they're not changing. But we will get more of these neutron decays. Okay? On average, we'll have half of these. So here we had 4, and after 10 minutes, on average, we'll have half of them decay, so we're left with 2. So again, that could be 3, it could be 1. It's a random process. Okay. 10 more minutes. Then we've got proton, 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 and then maybe 1 little neutron left. Okay. So we see that very quickly, as you go through multiple half-lives, the number of remaining radioactive or products that can decay decreases very quickly. Then after this point, we've only got 1. We can't say anything statistically about 1. So this little neutron here could last for 2 seconds or it could last for hours. Okay? So there's not much we can say about that remaining one. So this is why free neutrons are very rare in nature, because they decay away. They turn into protons. And a proton will quickly grab an electron, and that just becomes a hydrogen atom. So neutrons are rare. So, okay, so we already talked about this when we talked about electrostatic force and the structure of atoms, which is why the heck do nuclei stay together when the protons have such a strong electrostatic force repelling each other? Okay? And we talked briefly at that point about there's another force that must be holding them together in the nucleus. Okay? And that force is a new force, which is extremely important for nuclear physics. And that is the nuclear or the strong force. So sometimes you'll hear it called the nuclear force. Sometimes you'll hear it called the strong force. Okay, and we know this is a strong force because it is keeping protons from flying apart inside of a nucleus. The protons are being repelled by the electromagnetic force, and we already know the electromagnetic force is already a very strong force, right? When you compare it to gravity, it's many, many, many orders of magnitude stronger than gravity. Okay? So the nuclear force is even stronger than that. It's able to hold protons and neutrons together in a nucleus. So let's write a few properties of the strong force. It is obviously an attractive force if it's holding the protons together. So it's an attractive force between all nucleons. Remember, a nucleon is just a name for neutrons or protons. Okay? Anything inside the nucleus is a nucleon, neutrons and protons. So this is an attractive force. And it acts not just between protons and protons, but it acts between neutrons and neutrons, neutrons and protons, and protons and protons. Okay, so it's a strong force that attracts all these different elements in any combination we have there of nucleons. Okay, so in this sense, okay, so in this case, neutrons and protons have the same charge. Okay, so remember we've talked about a number of different charges, and we talked about how mass is like a charge. Mass is basically characterizes the force between two objects with mass. And for electrostatic force, the charge characterizes how strong the electrostatic force is between two charges. Okay? We talked about that with magnetic poles, how we could define the poles as another name for a magnetic charge. Okay? So in this case, we've got a nuclear charge, and we're not going to define that in any detail. The only important thing we really need to know is that the nuclear charge is identical for neutrons and protons. So they attract each other just as strongly, independently of whether it's a neutron-neutron combination, a neutron-proton, or proton-proton. So in terms of the nuclear force, these are completely identical. Okay? They, of course, still differ from their electromagnetic charge, which is a different force, but the nuclear force is identical on these. Okay, so there is a very key property of the nuclear force, which is it's confined to act over a very short distance. Okay, so it's defined to, or a very short range. It is defined to a range of about 2 femtometers. I'm going to start using femtometers when we talk about nucleus. So that's 2 times 10 to the minus 15 meters. So it only acts over the nuclear size scale. Okay. So what does that mean? That means if we've got 2 protons that are separated by a distance that's less than 2 femtometers, then the strong force kicks in and they're going to be attracted to each other. Now, it turns out 2 protons by themselves are not particularly stable. We need to get some neutrons in there. But they still will feel that very strong attractive force by the strong force if they're that close together. Okay? But once those protons become separated by a bigger distance, okay, so if this is greater than that 2 femtometers, so once those protons become separated, then the strong force disappears, and those protons are going to repel each other very strongly with just their electrostatic repulsion from the fact they have identical charges. Okay? So the strong force only kicks in when these protons are very close to each other. Okay? Otherwise, those protons just repel each other, just like we already learned with the electrostatic force. Okay? And this is actually the key to understanding nuclear reactions and where we get nuclear energy from, okay, and where radioactive decays come from. So that's a very key point. Let me move that up there. Okay, so the electrostatic force will win out unless those nucleons are very close to each other, especially the protons. Unless those protons are basically touching each other, the electrostatic repulsion will push them apart. Okay, so for the nucleus, there's 2 forces that are balanced. There's the electrostatic repulsion, and there is the nuclear strong force, the attraction. And I say they're balanced, but I should be careful there. They are trying to balance each other, and whether a nucleus is stable or unstable depends on how well those forces are balanced, okay, for a given nucleus. So let's talk a little bit about nuclear stability. Here I'm talking nuclear stability at the microscopic level, not the global level. Okay. Okay, nuclear stability. So there is a balance between the electrostatic repulsion trying to push those protons apart. Remember, the neutrons are not electrically charged, so they're just kind of sitting there. They're not really reacting with the protons in terms of electrostatic force. Okay, but they are helping with the strong force, because all the nucleons attract each other together into the nucleus. So there are opposing forces in the nucleus. Okay? And so it might not be too surprising that for a nucleus to be stable, okay, which just means that it doesn't decay into other nuclei, that those forces have to be balanced, okay, throughout the nucleus. Okay? So nuclear stability just implies there's a balance, okay, between the electrostatic repulsion of the protons and the strong force attraction between all the nucleons. Okay, so just to be clear there, it's the protons that are trying to push the nucleus apart. Okay? The neutrons aren't involved in pushing it apart, but the nucleons are, the neutrons are helping in keeping the nucleus attracted. Okay? They are participating in a strong force, basically helping to hold those protons in that are trying to repel each other. Okay, so not all combinations of neutrons and protons are stable. Which is what leads to radioactive decays and us being able to produce nuclear energy. Okay? So, but let's focus a little bit first on the ones that are stable, okay, and why they're stable, and at what conditions they become unstable. So, let's just talk about the general trends. Remember, the type of element is defined by the number of protons. Once you have an element, the isotope of that element is determined by the number of neutrons. Okay? But not every combination of protons and neutrons is stable. So let's just talk about trends, or general trends in terms of the stability of nuclei. Okay. The first is the more protons we have in a nucleus, the more neutrons we have to have in the nucleus as well. Okay? This is because the protons are all repelling each other. Okay? So if we have a nucleus and we bring in another proton, that proton is not just acting on its neighbors, it's acting on all the other protons inside the nucleus. So it is basically increasing the electrostatic forces quite dramatically inside the nucleus, trying to push it apart. Okay? For that nucleus to remain stable, it needs more attractive force, okay, without providing more repulsive force, which means it has to have more neutrons thrown in to make it stable. Okay? So the general trend is that if we have a nucleus with more protons, as we add more protons, we have to add more neutrons as well in order to keep the nucleus stable. Okay, so without the additional neutrons, the proton repulsion is too strong, which will create an unstable nucleus. Okay? So this is just general trends. Now you might think, naturally, which is a good thought, that we could just keep adding more and more neutrons into the nucleus, right? So the neutrons are always attractive, and so if we just keep adding more neutrons, they're always just going to keep the nucleus more tightly bound. Well, it's a good thought, but that's not the way nature works. Okay? Remember that free neutrons are, they decay. They decay with a half-life of 10 minutes. Okay? What keeps them stable in the nucleus is actually detailed. It's a little bit complicated, but it's the detailed interactions with the protons in the nucleus. Okay? And so when we start getting more and more neutrons, the neutrons become more and more unstable. So we get to the point where if we add too many neutrons into a nucleus, the neutrons will decay. Okay, so which means that the nucleus becomes unstable. So nature has built in this sort of range of stable nuclei where we can add more neutrons to make it stable, but once we add too many neutrons in there, then the neutrons will start to decay away. Okay, so there's a limit to how many neutrons we can put into a nucleus for a given number of protons. Okay? So generally, I've already said that the number of neutrons is about 1 to 1.5 times the number of protons. We'll talk about that more in 1 second. So, and the last thing I want to point out is that above 83 protons. All nuclei are unstable. Okay, nature has this limit of how many elements can naturally occur without being radioactive. Now, we can make heavier elements in the laboratory, but we can't make anything that's stable, that's going to last. Everything above 83 protons is unstable. What is 83 protons? Bismuth? Bismuth. BI, bismuth, right? My chemistry's a little rusty. So everything above that is unstable. We can make those, but they're all will decay into something else over time. Okay, so there is a natural balance between the number of protons and the number of neutrons in a nucleus for it to be stable. And if we look at a plot of nuclei, then we can find what we call the line of stability. So let's make a little graph here. Don't freak out if I'm drawing a graph. Okay, so this is just going to be a plot of nuclei, where in this axis we have the number of protons, and on this axis we have the number of neutrons. Okay, so let me put some numbers on here. So there's 0, 50, 100, 0, 50, 100. Okay, so this is a plot that's just supposed to represent for a given element. Remember, the element is determined by the number of protons, so each point along this axis would represent a different element. Okay? And then the isotope is determined by the number of neutrons. So for a given element, we can have different points along here for the number of neutrons in there. Okay? So now, if there were a perfect balance, draw this line. So this is just a reference line where the number of protons is equal to the number of neutrons. Okay? That's just for our eye to follow. What we would find is for the lighter elements, the ones that have fewer number of protons in them, so carbon, silicon, lighter elements like that, that the line of stability, which combination of neutrons and protons is stable, follows this line pretty closely. Okay? So that means that for the lighter elements, we have equal number of neutrons and equal number of protons for most of the stable elements. It's not exact. It's just approximation. This is actually not a single line. This is sort of a fuzzy set of points of stable nuclei. Now, as we get to heavier and heavier elements, we get more and more protons, which means the repulsive force gets stronger, which means we have to have more neutrons in the nucleus to hold it together, to counteract that strong force. So we'll see for heavier elements that this line diverges, okay, and turns up, okay, and then it ends at 83 here, which I told you is the last stable element we could have. Okay? So for the lighter elements, we've got the number of neutrons is generally about equal to the number of protons. And then when we get to really heavy elements, there's a limit where the number of neutrons is about 1.5 times the number of protons. Okay? So that shows this curve turning up. Okay? So that means heavy elements have an excess of neutrons compared to lighter elements. And that's actually absolutely key for nuclear fission, right? Which we will be studying in the next class. Okay? This is why we are able to carry out reactions in nuclear reactors. Okay? And so let me just repeat that again. For heavier elements, we have an excess of neutrons in the stable nuclei compared to lower mass elements. Okay, so that, let's see. You guys may or may not have seen wall charts like this. So let's see, can you zoom in on this chart way? I don't know if you guys can see this very well. This is mostly just, I'm just going to give you an introduction to this, and you can go look this up on probably Wikipedia, I'm guessing. Let's see, Wei, can you focus in on this? Ah, there we go. Okay, so this is a very complicated looking chart, but all this really is this plot I already showed you on the board here. It's just the number of protons versus the number of nucleons. And on this plot, they've basically, since this would be a very long plot, if it went all the way up, they've broken it into multiple sections. So they've basically taken that line and stacked it on top of each other. But if you look at the plot like this, what you can see is that there are isotopes here that are characterized, they're colored gray. The gray ones in these charts mean they're boring, which means they're stable. Okay, those are all the stable nuclei. And then they've color-coded them by the radioactive ones by giving them bright colors to make them more interesting. And so this is a very important plot. It's the chart of the nucleides. It's a very important corollary to the periodic table of the elements, because this chart tells us for a given element which isotopes are stable and which isotopes are radioactive. Okay? So it's a very important addendum onto the periodic charts. It's a little bit more complicated, but basically it's just showing you exactly this plot that I just made. Okay? It's just this is the line of stability shown by the gray ones in here, and anything that has a color on it is a radioactive isotope, and the color characterized is that half-life. So the brighter colors in here are ones with shorter and shorter half-lives, meaning they're more radioactive. Okay, so let's switch back. Okay, thanks, Wei. We can switch back to the board. So those are the stable nuclei, which are the boring ones. Okay, now we're going to talk about the unstable ones, which is what leads to radioactivity. Boring but important. Fortunately, most of the world around us is composed of stable nuclei. Okay, so let's talk about radioactivity. Okay, this is just the result of unstable nuclei. Okay, and they're trying to decay down into, usually into a more stable state. Right? Not always, but generally. For unstable nuclei, there are different levels of unstable. There is minorly unstable and there is majorly unstable. Okay? So the half-lives can range from about 1/1,000,000th of a second, okay, for the very highly unstable nuclei, up to over 1 billion years. For very, very stable, for nuclei that are almost stable, but not quite. They're still not perfectly balanced. So, for example, uranium-235 has almost a 1 billion year half-life. So it is almost stable, but not quite. Okay, so let's see, wait, can we turn on the projector for this? Or turn this over to the projector? Okay, so what I got here is a little mechanical model of nucleus. So this is the strong force is represented by this little bowl here. You can think of this as a model for the nuclear force, which has a very limited range. Okay, so as long as these little ball bearings, which are all the nucleons, so the neutrons and protons, as long as they are within this range of each other, they've got the attractive force, which is pulling them back together. Okay, so nucleons have a balance of forces, though. And so they are a little bit more dynamic than just sitting there at the bottom. Okay? They are whizzing around each other. They've got energy. Okay? And you can see I just had a radioactive decay there. we just knocked one of those nucleons out of there. Okay? So what I wanted to actually start with was, let's say, okay, I'm playing a major deity here, pulling this nucleus apart. Okay, you can see with the number of nucleons there, which is pretty small inside this, it's a pretty stable configuration. I think I have this up too high. Turn this down a little bit. There we go. So these things are pretty stable. They're getting knocked around, but the well we have here, which represents a nuclear force, is keeping them all pretty well confined. Okay? So, problem is when we start adding more and more in here, then we start getting a lot more interactions in this nucleus. And even though the nuclear force hasn't changed, we get a lot more energy getting knocked around in there. Okay? And we should start seeing these things. Oh, I think I turned it down too low. Okay, so if we start adding more and more nucleons in there, so we're basically creating heavier and heavier nuclei, then I feel like a mad scientist here making these heavy, stable nucleus here. We should start seeing more and more decays where things get knocked out randomly. Oh. Do it. I told you, radioactive decay is random, right? So we can't predict when it's going to happen. So I'm about to empty this whole bottle in there. Might put somebody's eye out. There we go. Now we're getting a big heavy nucleus there. Okay, you guys can vote this the worst demo of the semester, I feel like. I've had worse. I could find worse. Okay. Wow, these are all stable. Let's give it a little more energy, shall we? I'm going to turn up the electrostatic force here. They were popping out like crazy at the beginning, weren't they? There we go. It's about time. Now they all come out. Okay. Okay, well, I think you guys get the basic idea. This is a random process, okay? But clearly, the more stuff we have in that little, stuck inside the range of that nuclear strong force, okay, the more likely we're going to get stuff that's ejected out of it. Okay? Okay, so radioactivity. So there's a range of different half-lives, but there are different reasons nuclei can be radioactive. And we've already seen it. They can either have too many neutrons, which means the neutrons start decaying, or they can have too many protons, which means the proton repulsion is too strong, which is pushing the nucleus apart. So, not surprisingly, there are different ways that the unstable nuclei can decay depending on whether they are unstable because they have too many neutrons or whether they're unstable because they have too many protons. Okay? So let's characterize the different types of radioactivity. And there are three primary types. The first is probably the most difficult to understand. And it's what we call the alpha decay. So there's alpha, beta, and gamma decay, which you've probably heard from science fiction movies, different types of radioactivity. So alpha decay, that's an A there, is the first one we're going to talk about. It's the emission of a helium nucleus, which might be a little bit surprising at first, okay, but I'll try to justify this to you guys why nature works in this way. So helium is an interesting element. It's got 2 protons and 2 neutrons. Okay? So it's very balanced in the nucleus. Okay? Those are very tightly packed, proton, neutron. Okay? And balancing each other. The helium-4 nucleus turns out to be very stable. It's a very stable structure. Right? So in some ways you can think about the bigger nucleus being composed of many smaller helium-4 nucleuses that are all attracting each other. Okay? It's a very stable substructure of the nucleus. Okay? And so the fact that it's so stable means that when radioactive decay occurs, one of the common modes is to kick out an entire set of 2 neutrons and 2 protons just because they are so stably bonded to each other. Okay? So, and this has the effect in general to increase the neutron to proton ratio, which might not be obvious. Well, let me justify that. Okay. So this is a radioactive decay that will tend to increase the neutron to proton ratio. So if we have a nucleus that has basically too many protons in it, so the repulsive force is too strong, it'll often decay by kicking out a helium-4 nucleus, okay, which will increase the number of neutrons to proton ratio inside the remaining nucleus. So let's do a specific example of that, which is good old uranium-235, which is our key to nuclear energy. So uranium-235, I already told you, has a half-life. It's not completely stable, but it has a very long half-life. It has a half-life of about 700 million years, so almost 1 billion years, so a very large fraction of the age of the universe. Okay? But it's not quite stable. It will decay, and it decays by an alpha decay. So it will turn into a 231 thorium plus a helium nucleus. Okay. And that's with a half-life of about 700 million years. Okay, and it will decay by this mode because it has a shortage of neutrons, or you can think about it, it has too many protons in the nucleus to be completely stable. Okay? So let's look at the neutron to proton ratio. So for uranium-235, it's got 143 neutrons and 92 protons. So that ratio is 1.5543. Okay? And for thorium-231, this neutron to proton ratio is 141 over 90, which is 1.5667 when you put that in your calculator. So you can see that the neutron to proton ratio has gone up because of this decay. Now the reason for that is, remember that heavy nuclei have, in general, more neutrons than protons. Okay, so if you eject out a helium nucleus that has 2 neutrons and 2 protons, then you're decreasing the relative number of protons by a bigger effect than you're decreasing the relative number of neutrons, right? Because it has more neutrons to start with. So if you only kick out 2 of those, when you kick out 2 protons, you're kicking out a larger fraction of the protons than the neutrons. So you are increasing the neutron to proton ratio, which will tend to make the nucleus more stable if that ratio is too low to start with. Okay, so that is why a nucleus will decay by an alpha, okay, emitting an alpha. Now let's talk a little bit about the characteristics of an alpha decay. So this radioactive decay, which produces this helium nucleus, okay? So that helium nucleus will go shooting out. So that is the radioactivity that is coming out of this. But helium is very easily stopped. Helium-4 is a heavy nucleus. Okay? It will stop in a very, very small amount of material. So for example, it will not penetrate your skin. And if it's coming through the air, it'll tend to stop in air. So this is not the most dangerous of the radioactive decays. It's easily stopped unless it's swallowed. Or breathed in. Right? If you get an alpha emitter either in your stomach or in your system or into your lungs, then those alpha decays, which were stopping primarily in air, are suddenly stopping inside of the tissue in your body, and it can be very damaging. Okay? So these are generally not very dangerous unless somehow they've been ingested, in which case they can produce a lot of damage from having these heavy nuclei flying around. But they have some practical applications. There are alpha emitters in most smoke detectors. And they're commonly used to power the batteries in pacemakers. You don't want to implant a pacemaker in somebody that you need to change the batteries every day or so. So they fill them with little alpha emitters that decay with very long half-lives. And the energy from those alpha emitters actually power the decay. So let's see, how much time we got? Oh, good, we're good. Okay, so that is, those are alpha decays. Let's talk about the other decays. Besides the alpha, the next one is, not surprisingly, beta decays. And those tend to do the opposite effect to nuclei, so they tend to decrease the neutron to proton ratio. So these are named, by the way, in the order they were found. They were unknown quantities, so physicists, being very uncreative, gave them Greek letters. Okay, so alpha's first, beta second, gamma's third. Okay, so beta decay. So beta decay is the emission of an electron from a neutron decay. Okay, so this one is probably easier to understand. We've already talked about how a free neutron will decay, and if you get too many neutrons inside of a nucleus, then that force that's keeping them from decay gets diluted, and so the neutron will decay. So the neutron decays into a proton, which remains in the nucleus, plus an electron that gets ejected out. Okay? And it's this ejected electron which is what we characterize as the beta decay. It's the radioactivity coming out of a nuclei that has decayed. So this obviously has the effect of, since it converted one of the neutrons to a proton inside the nucleus, it has the effect of increasing the protons, relative number of protons, right? But decreasing the neutron to proton ratio. So this is if there's too many neutrons in the nucleus, this will convert one into a proton and make it more stable. Okay? So it will do the opposite. It decreases the neutron to proton ratio. Trying to make the nucleus, or the resulting nucleus, the resulting product, more stable. Okay, so that is, that's beta decays. In some ways, it's similar to alpha decays in that you have a charged particle that's coming out. In this case, it was a heavy helium nucleus. In this case, it's just an electron. Okay? So, but electron is a very light particle, and it's very easy to stop. So it takes a little bit more material than the alpha decay does to stop, but not very much. And so beta emitters tend not to be particularly dangerous as well, unless for some reason they are swallowed or breathed. Somehow they get ingested into the body, in which case that emission, the only thing that can stop it is the tissue in your body, which can be dangerous. So, but that also means if you're dealing with materials that are alpha emitters or beta emitters, it's really easy to shield them. Okay, so there's not necessarily a danger to humans interacting around them or working with them, unless they somehow get ingested. So the primary means of safety for working with these type of radioactive nuclei is to not get them on your hands, and to make sure that you're not in a position where you're breathing them in or somehow ingesting them. Okay, the third one is gamma decays. And gammas are very different from those other two. Okay, gamma decay is the emission of a gamma ray. Okay, and a gamma ray is just a very high energy particle of light. Or very high energy photons. So we haven't talked about photons yet. We'll be talking about those and quantum mechanics when we come back from Thanksgiving. But the important part here, you guys have probably all heard of photons. Okay? Photons are just particles of light, and a gamma ray is just a very high energy particle of light. Okay, so it carries energy out of the nucleus, but it's not carrying any particles. It's not carrying a neutron or a proton or electron. Okay? So what a gamma decay does is it releases excess energy. In the nucleus. But it doesn't change the nucleus itself. Or it doesn't change it otherwise than releasing that energy. Doesn't change the number of protons or the number of neutrons, so it's not changing the isotope. It's not changing the element, it's not changing the isotope. It is just releasing energy out of the nucleus. So it's got too much energy in there, it makes it unstable, and otherwise the nucleus would be stable if it kicked out that excess energy, which is what it's doing by kicking out a gamma ray. So gamma rays are different from the other two types of radioactivity because they're not charged particles. So it's the fact they're just photons of light, but they're very high energy photons of light, which means that they are much harder to stop. So those charged particles are very easy to stop in matter just because the electrostatic force is so strong. But gamma rays are much more penetrating, so it takes a lot more matter to stop them. So they are much harder to shield. So they can be very penetrating. For some of them, you're talking about literally inches of lead in order to stop the gamma rays. Okay? Whereas here, you might be talking about a piece of paper can stop alpha rays and beta rays. Okay? So gamma rays are much harder to stop, which means we call them penetrating radiation. But the fact that they're not charged particles, ripping through your cells, they're just single photons, means they're also less damaging per decay. So you can get exposed to gamma rays, but the gamma rays that enter, for example, your body will do a lot less damage than alpha particles or beta particles in your body. Okay, so they are much less damaging per decay, okay, but they are much more likely to penetrate into your body. And there are a lot of applications for gamma rays. One very practical application is that they are often used as tracers for medical imaging. So, for example, if there's certain reactions that you want to follow in the body, like in your thyroids or something, then if there's a reaction that uses a normal chemical, then doctors can put in isotopes, so radioactive isotopes that are gamma emitters into the body, and then the body will use those because they have the same chemical properties as the normal stable elements that are in those reactions. So that means they will follow the reactions through the body, but they're emitting gamma rays the whole time. And we have clever ways of imaging these so that we can see where these radioactive tracers are going through the body. Now, why they are emitting radiation, they are doing a little bit of damage to the tissues, okay? But there's always a trade-off between how important is it to find out what's going on internally, and is it worth doing a little bit of introducing a little radioactivity into a person's body in order to find out what processes are really going on. So gamma emitters are the ones that are usually used in medical imaging. Okay, so there are lots of radioactivities in the world around us. So turns out everything around us is radioactive to some level. Okay? So I've got a Geiger counter here, which is basically just measuring individual radioactive Ks. It's primarily measuring gamma rays just because anything else here would have to travel through the air to get to it. Okay, so you can hear each one of those little beeps. That's just coming from some natural background radiation. Okay, there is radioactivity naturally in soil, for example. Concrete turns out to be pretty radioactive. So for my research, I actually build detectors that detect radioactivity to look for nuclear processes going out in space. So these are telescopes that study nuclear reactions. But on the ground, what I see primarily is concrete. That's what we measure. Concrete is a naturally radioactive element. It's the potassium, which is also in bananas. So bananas are radioactive. Isn't that cool? But at a much lower level. So the radioactivity in just nature around us is generally about 1/2000th, depending on your specific location, of anything that would be fatal. So it's a very small fraction. Okay? Now there's man-made radioactivity, right? It comes from, you get this whenever you get an X-ray at the dentist or at the doctor. Okay? And just some products just naturally have radioactivity in them for different reasons. So here's here are two sources. This is a strontium-90 and a cobalt-60 source, both of which are gamma emitters. So, and these are radioactive. You can hear that when I put this up close to that you can hear the background. Okay. So fortunately, the best way to shield yourself from any radioactivity is to stay away from it. So you can see even though this is radioactive, if I hold it over here, you can't hear it interacting very much. So distance is your best friend when you're dealing with radioactivity. So this is a beta ray source. So remember, beta rays are not very penetrating. So they don't penetrate air very well unless you get it very close. So not too impressive. This is probably an old source. It's probably decaying away. Mantles, lantern mantles that you use when you're camping, actually radioactive. I think this is, I forget what it is in the mantle. I'll have to look that up. Somebody Google that and look it up for me, and we can talk about it on the forums. Why my mantles and camping lanterns are radioactive. Okay. Watches, okay, they used to put radioactivity on the radioactive nuclei on the arm so you could see what time it was in the dark. Okay. Maybe not the best idea in general, but it's pretty clever at the time. There's a lot of, there used to be a lot of radioactivity in different types of pottery. Okay. So you can see this plate is a little bit radioactive. Okay. Not too bad. It's probably decayed over time. Okay. But we actually have a lot of exposure to radioactivity just naturally. Okay. And it's generally much more than we get from man-made processes. So man-made processes in the world around us tend to be about 1/10 of the level of just our natural exposure of just us existing day to day in a world where there's always radioactivity around us. Okay. So, but that doesn't mean that there isn't the possibility of much more acute exposure, especially if this was, of course, an issue for nuclear energy and the safety involved, which we're going to talk about next time. Let's see, was there a question over here? Uh-huh. Uh-huh. So the question is, if somebody was undergoing chemo, would the Geiger counter pick that up? So I'm trying to remember the exact processes for chemo. I have to say that it's escaping me right now. That's a combination of chemical and exposure to radioactivity. So just by being exposed to radioactivity, you don't become radioactive. Okay? And so, so I think most chemotherapy, it's a combination of introducing chemicals to sort of make the cells more susceptible to radiation damage, and then they actually radiate the cancer cells with X-rays and gamma rays. Just the fact that it's getting hit by X-rays and gamma rays will not make it radioactive itself. So the goal there is just to damage the cells themselves. So now if you're doing some sort of medical imaging where you're introducing isotopes in to the body, then absolutely, that's the whole point, is that the people will become more radioactive. So yeah. Which isotopes to use for the atomic number? Oh, for the, you mean if they're doing medical imaging?
Or just for like, they have the weights on all the
Uh-huh.
right? That's a certain number of protons and neutrons.
That's right. Which isotope to use? So the question is, how do they know which isotope to use for different? It depends on what you want to do. So for example, if you're doing medical imaging, and iodide is a very common example of this. So there's different isotopes of iodide that have different half-lives. So really what you want for doing a medical image is that you want something that decays over the course of maybe a few hours, so that you can get in there, do your medical image really fast, and then the isotope decays out of the body and goes away. So yep, exactly. Okay, next time we're talking about nuclear weapons and nuclear energy. So picking up where we left off here.
I think Big Ben theory